Go to the launcher and click the Calculate Relative Flux button. And then that should make a notebook called or Calculate Relative Flux. So run all of the cells. Where it says select your photometry file, you want to select the file that's called photometry.ecsv. Hit select, and then for your aperture file, you're going to select source locations.ecsv. So that file has a list of all of the places where the colored circles were drawn around the stars in Notebook 2. And then click Add Flux Column, and it's done. What's changed on the left is that there's now a file called photometry relative flux.ecsv. That's added a column for each star with the ratio of that star's light to combination of all the other stars' light. Next up, we're going to do initial exoplanet model. You'll just run the first couple of cells till it asks you to select your photometry flux file. You want the photometry relative flux that just got made. Then hit select and it will load that. Then it wants you to select the information about the test object that we're looking at. So that's the tick or whatever.json. And if there was more than one filter in the data, it would want you to choose which filter to use. There's only one in this data. So you should end up with a plot like this. So the blue dots are the data. The red lines are showing when the transit was supposed to start and end. The yellow curve is showing the best fit to the data of a curve that's shaped like an exoplanet. The horizontal axis is time in days. So this is going, what is that, 0.06, 0.07 days, which is a couple hours, I think. Vertical axis is set so that its value is 1 when you're outside of the transit and is whatever it is elsewhere. I don't know about you, but I'm looking at this and I don't necessarily see a transit in there. It's a line, but it doesn't look super convincing to me. The last couple of cells you can run, but we're not going to use them right now. Now let's go back to the launcher and do the second exoplanet model fit. And this one, do the first couple of cells again. Select the same things you did last time. So there's a lot going on here. The blue dots are all of the data points. The red dots are the data points after they're grouped together in bins of 5 minutes. One way that you reduce the scatter in the data is you average data points together. The dots and green line are showing the bin data, so the red data points, after removing any correlation between those data points and a few other factors, and we'll come back to that in a minute. And then the green line is the best fit transit model to that. Let's go back up here. Up towards the top, right underneath where the widgets are, there's a cell for fit settings. And change the bin size from 5 to 10. What this is going to do is end up averaging more data points together. Let's run again until we get back down to the plot. Now, do you think there's a transit? It looks a lot better, doesn't it?
Yeah.
It's kind of remarkable that blue mess actually does seem to have a transit in it. On the right side, it looks like the transit ended roughly when it was supposed to. If everything lined up perfectly, the green line would be flat here. It would start to go down, dip, and then be back up by the time we get to there. Originally, it was dividing all of the data points up into groups, where each group was corresponded to 5 minutes of time. When we changed it to 10, it was doing that for 10 minutes of time. And, we could increase that. We can make it 15. But at some point, like imagine you made it 100, and then you might only have like 3 data points. You won't be able to conclude anything there either. There's a couple of other things that we can try. Down at the very bottom here, there's a whole bunch of information, and the legend for that is up here on the graph. So the sort of bluish line that's changing, it looks like a smooth curve, is the air mass. And so here the star was down lower in the sky. Here it was up higher. The gray line, I think, I have to go back up and look, is how wide the star is on the chip. So as the focus changes, how big the stars are will appear to change. It's not that unusual for the focus to change in the beginning part of the night because the telescope's still cooling down. The yellow line is the amount of sky background per pixel. It's not unusual for there to be, even after you've done this difference, to be some correlation between either the brightness of the star and what air mass it's at, or the brightness of the star and the size of the star, because that affects how much of the star's light is getting into the aperture. One thing we can try is if we go back up to the settings again, and where it says fit air mass right now, just fit air mass equals false. Let's change that to true. What we're telling the computer to do is, to the extent that there's a correlation between the air mass and changes in brightness, to remove that correlation from the data. Mine looks about the same as it did before. Let's go back up and try changing that back to false, and try changing the fit SPP to true. That's fitting the sky per pixel background. That's the sort of thing that would help remove any aurora effects that didn't get taken out when we did the flux ratio. Also didn't make any difference. Let's change the fit SPP back to false. There's a danger if you turn on too many fit factors. If you make a model that's complicated enough, it can fit any data. You want to try fitting the data with as few parameters as you can. We should be able to do fit underscore width equals true. Let's try adding that in, see if that makes a difference, because the width of the star was the only thing that looked a little bit different to me at the beginning of the fit.
What it would change if we change the fit of this, the width of the star?
So now what we're saying is, if the size of the star in the image is changing over time, but apparently that is not our problem. I'm going to go back and turn off the fitting. One other thing we can try here is, instead of keep transit time equals fixed equals true, let's make that false. The three things are the keep thing. The radius of the planet ends up being related to the depth of the dip. The radius of the planet's orbit around the star ends up being pretty closely related to how long the transit lasts. The transit time is when is the center of the transit. Sometimes we don't get a whole transit. We end up with just the beginning or just the end. And so in that case, we really cannot fit for the time because we don't know when it started. In this case, we do have both sides. So let's see what we get if we do that. That's not any different, is it? At this stage, there's three things that can happen. Two of them are easy. One is the data just looks like a mess no matter what you do. We didn't see a transit. Or the data follows whatever the fit line is pretty closely. In which case, excellent, there was a transit. Most of the cases seem to end up like this, where it's like, okay, I think something's happening there. Like, I don't think that's just a coincidence. On the other hand, that's weird. A couple things to do next. So there's one more exoplanet fit we can do. So go back to the launcher and do the exoplanet model fit with exotic. And you'll run the first couple cells, and you got to do the same selection that you've already done 3 times, or 2 times, or however many times. Then you can go ahead, whoops, right, we've got to fix up the video. So keep going until you get to this. Then click on candidate. And what we're going to end up putting in here is a bunch of information that this program called Exotic uses to do a more sophisticated fit than we've done so far. And sometimes it can do a pretty good job of pulling an exoplanet signal out where the first 2 things we were trying fail. We're going to have to look some of this stuff up. Let's go to this link. And we're going to need to copy paste the tick ID number, the 353 whatever, into that search form. There's a ton of information here about the star. The code I wrote has already gone to this website and pulled out some of the information. That's where it got the star's temperature, for example. What we want to look up is the ratio of the planet to the star radius. If we go back here and look under planet parameters, you're going to see that we've got a radius in terms of radius of the Earth. Let's see what we have for the star. So we can get the ratio of these two. It's just that they have different units. We want the size of the planet divided by the size of the star. We've got a radius here, but that's in terms of the radius of the Earth, of the planet. For the star, we've got a radius in terms of the radius of the sun. Sometimes Google will save you here. Let's do whatever the planet radius was. Radius of the Earth divided by 0.81 times the radius of the sun. I really love Google. We have a way we can check this in a second, and we'll do that. For now, it's 0.09575. We need to put in an uncertainty in that for that also into the box below. Looking at the data here, I don't see any uncertainties, and so what I do when I'm not sure is I just assume it's 10%. For the ratio of distance to the stellar radius, we can check here. I don't really see anything here that's going to get us that orbital radius, but if we go back to this fit, it came up with the value A over R star here is the planet ratio of the planet orbit size to the star's radius, and so that was 7.3963. So we'll use that here. Again, I don't know what the uncertainty is, so I'm just going to divide by 10. The star's temperature is here. The temperature uncertainty is probably not 1. There's the star effective temperature there. Temperature is 6,047. And then it says the uncertainty is plus or minus 1. If you look over here, though, it looks like the star's temperature is 6,047 plus or minus 64. It'll be plus 64 and minus 64. We have to put in the exposure time. It's 90 seconds. Let's put it 90. We forgot to fill in one thing. We have to fill in what filter here. So the filter we're using is SR. Then click in the cell below that again. Copy this. Paste it into the cell below and shift enter. To interpret what's going on here, on the left, there should be an exotic output folder. They wanted either blue-green filter or an infrared filter, and I did a red filter. But
Well,
are
we gonna retake the data or just say there's nothing here?
so for this particular one, for now, there's nothing we can do. Like, I think there is a transit there.